Bismillahirrahmanirrahim. Routing Information Protocol, RIP. Now, before I go on to explain this protocol, there's one thing I have to clarify. This protocol is very famous and it has got variations. Okay, it has got variations. There are different improvements that have been done to RIP, and some of them are very notable. But as we are doing these videos from the exam point of view, I am sticking to what is there in the text. Okay, so while different versions of RIP can operate in different ways, this video will focus mainly on what's given in the text, okay, from the text point of view, because it will help you studying for your exams. So beginning, we have RIP, the Routing Information Protocol. It is based on distance vector routing, okay? The ones we studied early on. And in RIP, the routers will advertise the cost of reaching to different networks, okay, instead of reaching to different nodes. So in distance vector, when we calculated the vector itself, right? When we calculated the vector, we were looking at nodes, right? There were nodes in here. However, in RIP, we are looking at networks instead of nodes. And the cost that we consider is the number of hops, okay? The number of hops. So here is how it works. If we are finding the number of hops from R1 to destination N4, which is in network N4, there will be 3 hops, 1, 2, and 3. Okay, so this is how it works. Similarly, it'll be 2 hops from R2, N3, N4, and 1 hop from R3 to the next one, which is N4. Okay? This is something you have to remember, is that this is still considered 1 hop. But in this case, there is no next router. Okay? It's a hop in distance, but there is no next router. So when we're making the tables, this is how it will look. So for router R1, we have, if we want to go to N1, there's no next router we need to go to because it's directly connected to R1, and the number of hops is 1. N2, same thing, no next router, 1 hop. N3, 1, 2, so, and the next router here is R2. We can only reach N3 through R2, and this is what we've given here. And to N4, it is 1, 2, 3, and the next router again is R2, 3 hops. And similarly, you go on to make the forwarding tables for R2 and R3. Now we are looking at the message format, okay? What do we have inside the RIP packet? The first 8 bits cover the command. This can be a request or a response. If it's a request, it means the router is requesting routing information from other routers. And if it is a response, it means the router is responding to the request. Okay? So this could be based on this field. It can be a request packet or it can be a response packet. We have the version 1.1, 1.2, and the current version is 2. Reserved, this is for reserved purposes. Family, what family of protocol are we using? Are we using TCP/IP, for example? And if it's TCP/IP, then this value will be 2. Tag, Now this tag will give the unique identifier for the autonomous system. Okay, to give the unique identifier. Now this whole thing will be repeated, and repeated based on how many entries we have in the routing table. Okay, so in this message we are actually sending the whole routing table. We're sending the entire routing table. Okay, so this is really what we're sending here. So what do these other fields indicate? The network address, okay, that's the destination address, the subnet mask associated with it. Now the next hop address, it's not really the address length. The next hop address will give you the next, if there is a router that is a better choice, the next hop address will give that information. For example, there could be a router, okay? There could be a router. So we're having this set of routers, okay? Now among these, this router R could be one that is actually not using RIP, okay? But instead of going like this to reach the destination here, considering these are too far away from each other, okay? Instead of going like that, it would be easier. So even though this is not using RIP, it would be easier to go in this way. So this is what it does. It gives you the next hop address, the preferred router that we could use, okay? And the distance will give the number of hops to the destination. So this is the RIP message format. Now, certain rules that we have to remember about RIP. There are some modifications over the distance vector algorithm. In the distance vector algorithm, we have routers exchanging vectors, right? They're exchanging vectors with their neighbors. But in RIP, instead of sending the vector, we are sending the whole contents of the forwarding table, everything that we have. We just send the whole thing off to the other routers, okay? And how does this work? Now, this is the version that we are taking that is in your textbook, okay? And based on that, this is how it works. So if we have router A, B, and C, okay, when A receives a packet from B, an update from B, okay, when A receives an update from B, it will, in its routing table, it will add to that route the next router it will put as B, and it will increment the number of hops, okay? So for example, if the destination is D, okay, so if we want to reach D, then because the packet, how does A come to know about D? Through B, right? Because B is D's neighbor. A is not D's direct neighbor. So A comes to know about D from B. So when A receives the packet from B, it will put the destination D, and because it has received it from B, it will put the next router value as B, and in B's case, the number of hops from B to D is 1. So what A will do is it will increment it to 2. Okay? So this is how it will update. So the entries that it receives from B, this is how it will update that entry. It does not have a route for D, so when it sees the route of D coming from B, it will put the next router as B, and it will update the number of hops as 2. So the receiver will add one hop to each cast and changes the next router field to the address of the sending router. Okay? Now, when do we select old routes and when do we select new ones that are advertised to us? How do we know? When do we select a new route and when do we not select it? Look at the first rule. It says the received route we select, in the case, the first one is, if the received route does not exist in the old forwarding table, then it should be added to the route. In this case, we have A, whose neighbors are B and C. And then, so A's routing table is initially looking something like this. Okay, this is A's routing table. So you have destination B, next router, there's no next router, and the number of hops, 1. You have C, next router, no next router, it's directly connected, number of hops, 1. Okay, for B, number of hops, 1. For C, number of hops, 1. Now, when it receives an update from B about D, does it have an entry for D here? It doesn't. So it will take in D. Okay, it will take in D accordingly. So this is what the first rule means here. If the received route does not exist in the old forwarding table, then it should be added to the route. Number 2, the cost of the received route is lower than the old one. In this case, the received route should be selected as the new one. If we have, in this case now, we have A. So let's consider this scenario where we have all these routers, okay? A, B, G, H, K, L, Z, okay? And we have another one, M, in here. So from A to Z, we have 1, 2, 3, 4, 5 hops, right? Number of hops to Z is 5. So in A's routing table, we have an entry for Z. The next router is B, and the number of hops is 5. However, if we have a new route that is developed through M in this way, now A receives an update from M about Z. Okay, it already has the entry for Z, but now it's receiving an entry from M, which is saying that Z is now 1, 2, 3 hops away from A, which is less than 5. So in this case, do we accept the new route? Yes, we do, because the next router is different, okay, and the number of hops is, in case of M, 3. So when we receive the update, we accept this route. And then it says the cost of the received route is higher than the old one, but the value of the next router is the same in both routes. In this case, the received route should be selected as the new one. Now, in this case, we have, again, router A. This is M, N, C, okay. So initially, the number of hops to M was 1, 2, 3, 4, okay? 4 hops to M. But let's say something goes wrong in this route. Let's say B goes down. And then C goes off to find another route to M, okay? It's finding another route to M. This route is longer, okay? So if we were to consider from A, it would be 1, 2, 3, 4, 5, 6, 7 hops, right? From A to M. When it receives an update from C now, A will see something like this. M, the number of hops is 6 because it is from C, not A. Okay, so now from C it is 1, 2, 3, 4, 5, 6, 6. And A already has an entry with 4. But because in this case it is coming from C, who initially gave 4, but now C is giving 6, because the next router has not changed, we accept the new longer value. Okay, because this means that something has gone wrong in the old route and we are now routing through another route. And the new forwarding table will need to be sorted out according to the destination route. So we will need to arrange them according to the route. Now this is an example we are using to show how RIP works. R1, R2, R3, R4, they are connected to different networks. So R1's forwarding table, N1, N2, N3, and there is absolutely no next router because it's directly connected. R2, again, N3, N4, and N5, all with a cost of 1 hop. R3, 2 networks, and R4, similarly, 2 networks. Okay, this is what we will see when all the routers come up. Now, this is the old routing table for R1. Okay, and R2 now sends its routing table, it's advertising to its neighbors, right? So this is R2. R2 has the information about N3, N4, and N5. N3, we don't have to worry about it because R1 already knows about N3. It is directly connected to it. So we don't worry, we don't take that value. But when they exchange information, okay, when R1 sees R2's forwarding table, here, it's not going to accept N3 because it has already got a value for N3 which is less. It will take N4, but before it takes N4, okay, in here, it will update the values, okay? So it'll say N4, R2, and the number of hops, okay? And similarly, it'll take N5 and it will enter the same details. So now it has information about N4 and N5 also, both through R2. Okay? So the next router is R2. If we want to go to N4, okay, and the number of hops will be 1, 2. Okay? Remember, in this case, are we going through the network? No, we are not. We're going through the router. It's the router that will have the routing table. This is why we're not considering the hop for N3. Okay? We're considering R2 and then N4. So 2 hops. Now, similarly, we have the same thing repeated for R3 when it sees R2. So it has N4 and N6 already, and it was now getting the values for N3 and N4. Okay? Sorry, N3 and N5. It's not N4 it's getting the values for. It is actually N5. And it will update the values accordingly. So as you can see now, R1, R3, and R4 have had their routing tables updated based on the values they have received from R2. So this is the final table that we have for R1, R2, R3, and R4. If you look at R2, destination N1, the next router we need to refer to is R1, and the number of hops is 1, 2. Similarly, if we want to go to from R2 to N6, then we go through R3, and the number of hops is 1 and 2. Okay, this is how you're working on this. So this was RIP, and in the next video we will look at OSPF.